let's talk about the angle between two vectors. So we have some vector here, u, we have some vector here, v. And so the angle between the vectors, this theta here, what can we say about this angle? Is there a way to come up with a formula for it? So we're going to do a little bit of exploration here to see if we can come up with a formula for it. By the way, everything I'm going to do here is just going to look like it's in 2 dimensions. It works just as well in 3 dimensions as in 2 dimensions. So yeah, so we want a formula for this theta as here. What things are we allowed to use if u and v are vectors? So obviously we can use u and v. This is a section on the dot product. What will the dot product tell us about the angle between them? So we can use u dot v. And really, vectors u and v, one information we can get from it is, of course, the length of the vectors. So I'll add the length of u and the length of v. I'll add that to our list of things that we can use in our formula. Okay, how I want to do this is that, there's a piece of paper sitting off the screen right now that has the formula on it. I could just show you the formula, but let's just play around with it a little bit to see if we can make some guesses here. So I'm going to do some quick examples here. So suppose our 2 vectors are I hat plus j hat and I hat. And I guess we'll just always suppose that this is u and this is v here. Okay, so the dot product of I hat plus j hat with I hat is going to be 1 times 1 plus 1 times 0. So the dot product here, u dot v, in this case is going to equal 1. And this theta here, well, it's pretty easy to see that this is a 1, 1, square root 2, a 45, 45, 90 triangle, if you will. And that angle right there is pi over 4. Also, let me just point out here the magnitude of u and the magnitude of v. Magnitude of u here is square root 2. Magnitude of v here is 1. And let me finally point out here that the cosine of pi over 4 is equal to 1 over square root 2. And so the thing that we should be realizing is that this looks somewhat promising here. We see 1s, we see a square root 2, and cosine of pi over 4 is 1 over square root 2. So maybe you start thinking about what's the appropriate way to put together all of this information in a formula for cosine of theta. It gives us something to do with these values here. Also, whatever we do should be symmetric in u and v. We interchange u and v. That shouldn't change anything. Let's do one more example here. So let's suppose that this is I hat plus square root 3 times j hat. And this is I hat. Again, this will be u, and this will be v. So now our triangle is going to be, the high school trick 30, 60, 90 triangle. 1, square root 3, and 2 are the lengths there, with this angle down here in radians is pi over 3. Once again, let's just write down u dot v, 1 times 1, plus square root 3 times 0 is 1. So u dot v is still 1 in this case. And magnitude of u is going to be, the length of u, as I already put here, is 2. The length of v is 1 here. And we know that the cosine of pi over 3 is 1/2. So again, we see this is very suggestive here. and we do u dot v over the magnitude of u, that checks out. Again, we want it to be symmetric here. So cosine theta, if we make cosine theta equal to u dot v over magnitude of u times magnitude of v, let's check this over here. That would be 1 over square root 2 times 1 over square root 2, that checks out. Over here, it's 1 over 2 times 1 over 2, that also checks out. And our formula is nice and symmetric. If we interchange u and v, we get the same thing here. So here is, let me make that a little bit neater here. Our theorem that theta be the angle between u and v. We'll make sure that u and v aren't equal to 0, because otherwise it's a little bit hard. It would be hard to define the angle between one vector and a 0 vector. Then cosine theta is equal to this expression, u dot v over magnitude u times magnitude v. I showed some motivation for this definition on the previous slide. I'll do a later video in this video set. We'll be showing you a formal proof. We'll give a formal proof of this. Okay, so let me make some commentary here. So the formula works in both 2 and 3 dimensions. And another thing is that, like, so cosine theta is equal to this expression here. I can take inverse cosine of both sides to give us the fact that theta is equal to arc cosine of u dot v over magnitude u magnitude v. And in fact, this is the book's definition of dot product. So my exposition here and the book's exposition are a little bit in the reverse of each other. The book starts off with this kind of formula here, and then churns out the dot product, the definition of the dot product, using multiplying together the components and adding up, adding up those products here. I'm doing it in reverse. I'm defining the dot product in terms of multiplying the components together and summing them up, and then pulling this out as a consequence. Both are fine. Let's do an example before we do anything else here. Let's do an example here. Find the angle between u is I hat minus 2j hat minus 2k hat. V is 6i hat plus 3j hat plus 2k hat. So in order to do this, we need magnitude of u. It's going to be square root of the first component here is 1 squared. The second component here, negative 2 squared. The third component here, so we have negative 2 squared. This would be 9 under the square root, so 3 after we take the square root. The magnitude of v here, so we'd have 6 squared plus 3 squared plus 2 squared for our calculation here. This is going to be 49 under the square root, so 7 here after we take the square root. Finally, we need u dot v, so that would be 1 times 6 minus 2 times 3 minus 2 times 2, and those cancel. We just left with negative 4. So now putting everything together here, so the angle between u and v is this formula here. So theta is going to be arc cosine of negative 4 over 3 times 7 arc cosine of negative 4 over 21. And that's not something that we can simplify. So this is a perfectly fine and preferred final answer. Okay, a couple more consequences to go through here in this video. So the dot product here is negative. The dot product here is negative. What does that mean here? So let me say here u dot v. So there's three cases that we could have for a dot product. That could be positive, it can be 0, or it could be negative. And each one of these three cases is going to tell us something about, each one of these three cases is going to tell us something about the angle here in a big overall qualitative sense. And that has to do with, well, if we go back once again to here, so the u and v, these lengths down here, those are never going to be negative, and they're never going to be 0, because these aren't the 0 vector. So u dot v, if we have cosine theta is equal to u dot v over something positive, well, u dot v is positive, cosine theta is positive. If u dot v is negative, cosine theta is negative. What does that tell us about angles if cosine theta is either positive or negative? Well, if the cosine is positive, that tells us theta is an acute angle. And so that is theta is less than pi over 2 radians. If u dot v is negative, theta will be an obtuse angle. Theta will be between pi over 2 and, pi over 2 and pi radians here. And then there's a final special case here. If u dot v is equal to 0, u dot v is equal to 0, cosine theta 0 over, who cares, cosine theta 0. When is cosine theta 0? That is, theta is a right angle. Theta is pi over 2. And the most important special case here, well, first let me just kind of point out here. So our dot product here is negative, so the angle is obtuse. So let me say here, the most important special case here is if our vectors, the dot product is 0. And it's so important that we have a special term for that. Two vectors u and w are orthogonal. So this is our special term here if the dot product of them is 0. So, we're used to saying things from high school trig or high school geometry that, the angle between them is a right angle. And so orthogonal is kind of the bump things up. So now we're talking about vectors here. We'll talk about orthogonal vectors right here if the dot product here is 0. So a final example in this video here, if we have a vector that is orthogonal, I should say here, what's the goal here? We have to find, that verb here, find a vector that is orthogonal to this w vector, minus I hat plus 2j hat plus 2k hat. So let's see here. We just need something that the dot product with w is 0 here. So let's see here. I could make u equal to 0 I hat plus 1 j hat minus 1 k hat. And in that case, I would have u dot w would be 0 times 1. 0 times minus 1 plus 2 times 1 plus 2 times negative 1. And sure enough, that's 0. There's lots of other possible answers here. I'll leave this as a take-home exercise for you to try to find some more possible vectors that are orthogonal to w. And to finish off this video, so to practice with these cosine calculations, please calculate for me the cosine of the angle between this v and this w.